In this video, we'll look at exponential functions and some characteristics of exponential functions. So in a previous example, we looked at the levels of medication that's present in a person's body and how it decreases over time until the time of the next dose. And so the function that models this would look something like this. It's an exponential function, and we call this exponential decay. We should write that down. So this is an example here of exponential decay. Decay because the amount is decreasing or decaying. And another sort of similar but slightly different example would be the number of generations in the past compared to the number of ancestors that you have. So, you would have two biological parents. Each of those parents would have two biological parents, and so on and so forth. So the further that we go back into the past, so as the number of generations into the past increases, the total number of ancestors that you have also increases. Again, this is exponential growth. You get kind of this doubling over time of the number of people. So this is what we call exponential growth. And certainly we see a lot of exponential growth when we talk about the spread of viruses and whatnot. Exponential growth. And just like other functions, exponential functions have some characteristics, and we're going to look at some of those characteristics now. So these are two examples of when you might see exponential growth or decay. Let's have a look at some characteristics. Before we do that, we need to talk about one feature. I don't know if you noticed here, but it sort of looks like this line is getting closer and closer to something, but never quite touching. Same with this one. It doesn't kind of abruptly stop, and so on. We have a special name for that. And we call that an asymptote. So an asymptote is a line that the graph will get infinitely close to, but that it doesn't actually touch. And I think on these graphs that might be a little bit more obvious. So for example, see if I can draw a line here. This line right here, in this case, maybe we'll use a different color other than red. The x-axis is a line that the graph is going to approach. It's getting closer and closer and closer to, but not actually touching. So we call that the asymptote, and that asymptote has an equation. So the equation of this line is always y equals whatever the y coordinate is, and in this case it's just y equals 0. So this has an asymptote of y equals 0 because the y value right here is equal to 0. Had the asymptote been up here, and the graph were getting closer and closer but never actually touching that, we would say that the asymptote there was just y equals 4. All right, let's identify some characteristics of this function. Graph A here, some characteristics. Right away, we can see that the domain, at least as indicated by the graph, this is the same graph or similar graph to what we saw on the previous page with the concentration of medication in a patient's body. So it's decreasing over time. But if we look at just the graph without the context here, we can see that the domain is that x can be anything. Realistically, there would be restrictions on the domain. At some point, there wouldn't be any medications left in the patient's body, and at some point, the patient hadn't taken any. But if we're just looking at the graph as a graph, we can say that the domain here, x is an element of the real numbers. Sorry, that's a really bad looking symbol. Let's see if we can fix that up a little bit. Should probably just start that whole line over. All right, so x is an element of the reals. For the range, remember the range is the possible y values. So the y values for this function basically start somewhere way up here, and they come down and get closer and closer to 0, but never actually touch. So we say that y is an element of the real numbers, such that y is greater than 0. We don't want to say greater than or equal to 0. We just want to say it's strictly greater than 0 because according to the graph, we're never actually going to get there. That line y equals 0 is an asymptote. Maybe we'll write that down in a second. All right, let's talk a little bit about the x-intercept or x-intercepts. There aren't any because this graph will get closer to the x-axis but never actually touch it, so there are none. There is a y-intercept though, and that y-intercept is 10. or we can write that as an ordered pair, 0, 10. And that y-intercept in this case would represent the amount of medication that the patient started with. So if it was 10 milligrams, the patient started with 10 milligrams, and over a certain number of hours presumably, that medication would dissipate. And then I guess we should talk about the horizontal asymptote. I think I'll just call it an asymptote for now. There are vertical asymptotes. We'll get into that a little bit later. And the asymptote is this line right here that the graph is going to get closer to but never actually touch. And we already talked about how the equation of that is y equals 0. All right, so that's graph A. Graph B is also a medication, the concentration of medication in a patient's body. Let's do the same thing. Notice here that the domain is going to be the same. X can be any value. Y can be any value as long as it's greater than 0. We still have this horizontal asymptote down here. The graph is getting closer and closer to, but never actually touching. The range is the same. There's no X-intercept. It has the same Y-intercept. So it looks like actually all of these features are the same. So maybe what we'll do is we'll just copy this. I don't know if I can do that. Nope. All right. We'll just quickly jot these down. So the domain is that X is an element of the real numbers. It can be anything. The range, as long as the Y value is greater than 0, we're good. So Y is an element of the reals such that Y is greater than, and is strictly greater than, 0. The X-intercept, again, there isn't one. There is a Y-intercept at 10, or the 0.010. And again, there's an asymptote, horizontal asymptote. And the equation of that horizontal asymptote is y equals 0. So these two graphs, although they look quite different, have the same sort of characteristics. So at some point we'll probably need some more details about how do we distinguish between these two graphs. So again, graph B could be a medication that's administered that maybe dissipates at a different rate. And you can see here that if you're the doctor and you want to administer medication to a patient, when the amount of medication in their system is less than 1 milligram, that would happen here after 4 hours if this time is measured in hours, whereas on this graph with this medication, it would happen more like after 23 hours. So things, although the graph has a lot of characteristics in common, it does have some characteristics that are different as well. All right, so that's a quick rundown of the exponential functions and some of their characteristics. Oh, I guess we didn't talk, sorry, I just realized we didn't talk about whether the graph was increasing, the end behavior. So maybe we'll just jot that down in here as well. We should probably do that. So the end behavior of both graphs will be the same. Whoops, there we go. So the end behavior here, basically as x approaches negative infinity, so what's happening as x gets big in the negative direction. So as x approaches negative infinity, so we're going to move from right to left here, the y value is going towards positive infinity. And as x approaches positive infinity, that's way out here, what's happening to the y value? Well, in this case, the y value is getting closer and closer to that asymptote, which is 0. So as x approaches positive infinity, y is approaching 0. And that's true for both of these graphs. So that the end behaviors here would be the same. All right, there's your quick rundown of characteristics of exponential functions.